You ever stop and wonder how we manage to feed billions of people on this planet? Well, the answer is kind of like modern-day magic. It's a process that literally pulls one of the most important ingredients for life right out of the air we're breathing. So let's jump right in and unpack this incredible story of science, food, and fuel.
Yeah, it really is mind-blowing when you put it like that. And this isn't some far-off sci-fi concept, This is the real deal, fundamental process that modern farming is built on. We're going to break down exactly how it works, step by step.
All right, so the whole story really kicks off with a paradox. The main ingredient we need to grow our food, well, it's literally all around us. It's in every single breath we take. But, and this is a big but, there's a catch.
Yep, 78%. Our atmosphere is just this massive, enormous tank of nitrogen. I mean, think about that. It's an almost endless supply of the number one thing plants need to grow.
So here's the problem. All that nitrogen in the air, what scientists call N2, is locked up tight. The atoms are stuck together with this incredibly strong triple bond, which makes it, well, chemically really stubborn. Plants just can't break it apart to use it. That analogy is perfect. It's like being surrounded by water, but you can't drink any of it.
So to crack this puzzle, scientists had to come up with a recipe, a way to force that stubborn nitrogen into a form that plants can actually absorb. And that recipe, it turns out, needs two key ingredients that we get from two totally different places.
Okay, first up we need hydrogen, and we usually get that from natural gas, stuff we pull out of the ground. And second, we grab that nitrogen right out of the air. So one ingredient from deep in the earth, the other from the sky all around us. So how do we get that hydrogen? Well, this part's pretty wild. We take methane, that's the main stuff in natural gas, and we basically blast it with super high-pressure steam. This whole reaction just rips the hydrogen atoms right off the carbon. And here's a really important detail to tuck away for later. A big-time byproduct of this whole step is carbon dioxide, CO2. Okay, so we've got our ingredients. Hydrogen from the gas, nitrogen from the air. Now we get to the absolute heart of the matter. This is the magic step, really. It's an invention that was so revolutionary it won a Nobel Prize. It's called the Haber-Bosch process. In this diagram right here, it's a perfect roadmap for how this whole thing works. You can see the basic flow, right? Hydrogen and nitrogen go in one side, and this brand new thing comes out the other. So let's really dig into what's going on inside that machine. So, to get those super stubborn nitrogen atoms to finally break apart and play nice with the hydrogen, you have to create a totally insane environment. I mean, just look at these numbers. We're talking pressures 200 times what we feel right now, and temperatures soaring to 450 degrees Celsius. That's hot enough to melt lead. It's basically pure brute force that makes the chemistry happen. So, let's follow the journey on our diagram. First, a massive compressor just squeezes those two gases, the hydrogen and nitrogen, together like crazy. Then they get pushed into the reactor where they pass over a special iron catalyst at that blistering hot temperature. And that combo, the crazy heat, the immense pressure, and that catalyst, it finally forces them to bond and create ammonia gas. The last step, a condenser cools everything down, turning that gas into a liquid we can actually use.
And just like that, we've done it. We've created ammonia. But, a giant tank of high-pressure gas isn't exactly easy for a farmer to use in a field, right? So the process isn't quite over. We still need to turn this amazing chemical into a stable, solid form.
Now, some huge industrial-scale farms do actually inject the ammonia gas right into the soil, but for the most part, it's just too difficult and honestly pretty dangerous to move around and handle. So for most of us, it has to be converted into something you can, actually hold in your hand. And that usually leads to two main products you'd recognize. The first is urea. And this is a really clever bit of chemistry. Remember that CO2 byproduct from way back when we were getting the hydrogen? Well, they react the ammonia with that to make these solid little granules. The other big one is ammonium nitrate, which is another solid pellet made by mixing ammonia with nitric acid.
Okay, let's just zoom out for a second. We've been talking about compressors and reactors, but what we've really just walked through is one of the single most important industrial processes in all of human history. Seriously. This chart here just lays it all out perfectly. You take the nitrogen from the air itself. You use natural gas, a fossil fuel, to get the hydrogen and the energy, and you combine them in a factory to make ammonia. That ammonia becomes the base for the fertilizer that, quite literally, feeds the world.
And you really can't overstate the impact of this. I mean, this single invention is one of the main reasons our planet's population could explode from less than 2 billion to over 8 billion in about a century. It's what stopped mass starvation. It completely changed the course of human history.
But a process this powerful, a process that uses this much energy, well, it doesn't come for free. There's a major trade-off, a really significant environmental cost to this magic trick of turning air into food.
Because the whole Haber-Bosch process needs so much intense heat, and because it all starts with methane, making fertilizer is just incredibly energy hungry. When you add it all up, it's responsible for something like 1 to 2% of all global greenhouse gas emissions. Now, 2% might not sound like a giant number, but for just one single industry, that is a massive, massive footprint.
So that brings us to the big question, right? Is there a better way to do this? And scientists are absolutely racing to find an answer. The front runner right now is something called green ammonia. The core idea is brilliant. You keep the genius Haber-Bosch part, but you ditch the fossil fuel. So instead of getting your hydrogen from natural gas, you use renewable energy, like solar or wind, to split water into hydrogen and oxygen.
And that really leaves us with the defining challenge of our time. The first formula was a miracle. It changed the world, it fed billions, but it came with a heavy price tag. The question now is, can we invent a new formula, a cleaner one, a sustainable one, to feed the billions yet to come? The race is on.